We talked last week about some of the basics of ANOVA, the theory behind it. And this week I really want to focus on the pragmatics of what you're going to be doing on the assignment for this week. Now, I created a video that's already been posted and you can follow along with those steps. However, I wanted to be sure to stress a few things that will definitely be on the test. So I'm going to tell you a little bit more about the actual project you will be working on, which is the Watching Paint Dry One-Way ANOVA. This is the exact same example as what you will see in the video. I'm going to give you a little more information, and it is also very similar to a one-way ANOVA that you will be doing using the data that I provided this week. However, the data that I'm using for this example, I have changed. So the outcome that you will see with this example, even though the setup looks similar to what you will see in your assignment, will not be exactly the same. A marketing major, redecorating his dorm room, finds 4 different paints advertised as fast drying. So as scientists, we want to know, does the marketing match the hype? So he gets 5 samples of each of the paints and records how many minutes elapsed until the paint was dry enough to apply a second coat. How long does it take for these paints to dry? So your assignment then is to use JASP, the alpha equals 0.05 level, to test whether the paints have different drying times. And if so, use a 2-key post-hoc test. So when you're using JASP, many of the beginning points will be exactly the same. For instance, in this example, you will always have the variables in a box, and you move the variables from their, let's say, storage container into where they go in a proper place in JASP. And what I wanted to remind you of is that JASP uses these shaded icons to indicate what type of variable goes where. So in our data set, we have a list of times, and we have 4 different types of paint. Keep that idea in mind, because as we get closer to the final, there may be data sets where you have to figure out what kind of analysis can I do with these data based upon what you're being asked to find out, what you're being asked to test for. Well, you need to know how a one-way ANOVA should be structured, how the data should be structured, so that you can do this test. That they will be structured the same way as for an independent samples t-test, where we have 2 variables. One is a scale variable and one is a categorical variable. And JASP always gives us that hint. Where do these variables go? So our scale variable goes in the dependent variables box with that icon for the ruler. And the fixed factors, in our case we have just one factor, is the type of paint, and we can see that's a categorical variable. The other things you want to ask for would be the descriptive statistics and the type of effect size. So always be sure to get those descriptive statistics and check the assumptions. So for the one-way ANOVA, the assumptions are going to be exactly the same as they were for the independent samples t-test. Be sure to check for homogeneity of variance, which you do first just by checking the box under assumptions checks for homogeneity. If that assumptions check comes back significant. So if the Levine's test is significant, less than 0.05 or less than 0.01, that means that there is a difference between the variances of the groups. But homogeneity means those variances should be the same. So when that test, when the Levine's test is significant, it means the variances are different. That is violating the assumptions of the test. Anytime that occurs, your alternative would then be to do a Welch's test. And in JASP, it's very easy. You just click on Welch as your new alternative test. But when you do that, be sure to keep that in mind. When you choose your post-hoc, you'll want to choose a Games-Howell post-hoc in order to follow up with your Welch's ANOVA. The procedure is very simple. You check your assumptions. Assuming the assumptions have not been violated, we just proceed. But if the assumptions have been violated, we have options. We're going to switch to a Welch's test, and we're going to use a Games-Howell as the follow-up. We also want to get a measure of effect size. And in this example, I've selected both eta squared and partial eta squared. The eta is the Greek symbol. It looks almost like an N. What you will note is that the eta squared and the partial eta squared are exactly the same for the one-way ANOVA. You can see that in the findings. They are both a 0.471. So they're exactly the same. What I tend to do with the one-way ANOVA is I just check the eta squared because it's there. It's easy to get to. But I always report them as a partial eta squared. And I'll briefly explain why, go into a little more detail about this effect size. The eta squared is the percentage of variance in the dependent variable accounted for by the independent variable. So it's how much of the difference in dry time is accounted for by type of paint. We would interpret this the same way we would with an R squared, which is the correlation squared. We're going to cover correlation actually in week 10, upcoming. And I'll tell you more about how we interpret an R squared. But it means exactly the same thing in that correlation as it does in this interpretation with our ANOVA. The problem with that eta squared is that it is biased and that it tends to be a little too large. It overestimates the true effect size. And so what the software will do is partial out some of the overlap in the variance. This would be if we had more than one independent variable, and give us a partial eta squared, which is still the strength of the association, still interpreted the same as an R squared. It's still the percentage of variance in the dependent variable accounted for by the independent variable. So it's still the proportion of dry time accounted for by type of paint. In the one-way ANOVA, they will be the same. Eta squared and partial eta squared will be the same. It's only when we start adding additional variables, additional factors, that the partial eta squared begins to change. This is the ANOVA summary table. And below the ANOVA summary table from JASP, which is the one at the top, I've included an example from SPSS. And I did this just to point out that JASP does not give us that third row, which are the totals. Now, why are they giving us the paint and the residuals, but they're not giving us the totals? It's because we're not really going to use the totals for the calculation of the F value or the significance, and so they've just left them out. You can easily calculate them. The total for sum of squares is the sum of squares between plus within. Same thing with degrees of freedom. So we have 3 and 16 degrees of freedom. Just add those together, it's a total of 19. So you could very easily get those numbers with some simple addition. And I mention that because on the assignment, there will be a place where you'll want to be sure to fill in the totals for each of those, sum of squares and degrees of freedom. The mean square is the sum of squares divided by the degrees of freedom. In this case, 573 divided by 3 gives us roughly 191. We do the same thing for the residuals. And then, remember the F ratio is the ratio between, variance between and variance within. So we would take that 191 divided by 40. That's where we get the 4.75, which tells us there's 4.75 times more variability between than within. So here's another important point that I want to make that could be a source of confusion, and I just want to make sure that it's not. And that is the way that different types of software represent the sources of variability, specifically what they call it. Now, as I've been explaining ANOVA, I've been using just the most basic of terms, between and within. But when we see the software, it may be listed differently. So for instance, with ANOVA, for the between factors, that's the types of paint, or the differences between the types of paint, they just tell you the name of the variable, which in this case is paint. And instead of within, they use the term residuals, which is the term that we associate with the general linear model or regression. So these are two very legitimate ways of referring to between and within, but it's a little bit different. In this example from ANOVA, we see between and within listed specifically, But this is actually a simplified version of the one-way ANOVA. If we use the full general linear model, it's going to call it not residuals or within, it's going to call it error. All of those terms are referring to the same thing. Variation within, variation for error, variance for residuals, all referring to the same terminology. Just trust the order of the rows. The top row is always between, second row is always within, third row is always totals for a one-way ANOVA. If we start adding more variables, obviously we're going to get more rows. When you write up your results for the ANOVA, where do those elements come from as you complete the write-up? And I just wanted to make sure you know where the elements are in the table and where they go in our APA-style write-up. So we always begin with the name of a test, in this case F. You notice the F is in italics because we italicize the name of the test. And then in parentheses we have degrees of freedom, in this case 3 and 16. And those come from the degrees of freedom column in our ANOVA summary table. The F value, round that to 2 decimal places, 4.75. The probability, if the probability is a number, write out the number. In this case, P equals 0.015. If the probability is listed as 0.00 or 0.000, you just say less than 0.01, less than 0.001. There we go. And finally, we see the eta squared, which I'm reporting as a partial eta squared. It's a 0.47. Again, rounding to 2 decimal places. So now you can see where the elements that go into our write-up come from in the ANOVA summary table. And again, we will be doing that for our assignment. In this case, our ANOVA was statistically significant, and so we need to follow up. Because the ANOVA tells us that there is a difference. One of those types of paint dries faster, but which one? That is what we really want to know. To answer that, we need to follow up with a post-hoc test. All of the post-hoc tests work essentially in the same way. It's telling us which of the groups is different, but there will be some variation in how the findings are displayed. So let me show you the simplest one, the one that we'll be using. It's called Tukey's Honestly Significant Difference Post-Hoc Test. It is the minimal difference between the means. You can calculate this from your ANOVA summary table. That minimal difference that is required for them to be honestly, significantly different. They will be different, but to be honestly significantly different, here's how much they have to deviate from one another. The formula that's being used by the software to calculate this uses a value called Q, which is a constant. It comes from a table. If you look in your notes, I've actually included a copy of this table that you could follow along and find this Q value that you would plug in. It's the mean square within divided by n sub k, which is just the number in each category, or the n for one condition. In the examples that we're doing in class, each group has the same number of people in it, which makes it very simple to do this. But if you were to have unequally sized groups, you would use the smallest, the sample size of the smallest group. So let's say we have 3 groups, and there's 15, 17, and 20 in each group. We would use n sub k of 15. Use the smallest group. We would calculate a value. And all I want you to see is that it's going to give us a number. In this case, it's a 1.98. That is Tukey's honestly significant difference. It's the minimum difference between the means that is required for true or honest statistical significance. Here's how you interpret that. We look at each of the means, and the good news is they're presented to us in a table, so it'll be really easy to make these comparisons. And we take each mean, we can subtract it from the next, and find out what's the difference between them. So for instance, we would start by mean 1 minus mean 2. What's the difference between them? Is it more than 1.98? mean 1 minus mean 3, mean 1 minus mean 4. And we would start over with mean 2 minus mean 3, mean 2 minus mean 4, and then finally mean 3 minus mean 4, always looking for differences greater than 1.98. If any of those comparisons is greater than 1.98, those two groups are different from each other. Sir?
Where'd you get 1.98?
That comes from this formula. Now, I will caution, that number will be different
Right.
for any particular ANOVA. So this is not, itself is not a constant. How would we do this for our example with JASP? Well, first, we would get our post-hoc test by simply moving paint, our categorical variable, into the box for post-hocs. So we twirl down the post-hoc test, move our variable over. Tukey will be selected by default, so we don't have to do anything. I do want to point out though, Games-Howell, remember if we did a Welch's test, we would use a Games-Howell post-hoc. This is where we'd select that. And I also want to point out something that I didn't show in the video. I just realized it myself. I should have included this. It is the flag significant comparisons option. That's going to just point out to us very clearly which groups are different. And then when you look in the findings or the results, you'll find a table that's doing all 6 of the comparisons. And so in this example, the paint 1 and paint 2, fast coat and hasty hide, those have a p sub Tukey, an honestly significant difference p-value of 0.009. And you see the 2 asterisks. That means that they are different at less than 0.01. That's how we interpret. And as you look at the remaining comparisons, no asterisks. None of those are different from each other. Now the challenge when you have 6 comparisons is conceptualizing, this one's different from that one, but it's not different from this other one. This is why I always get a descriptive plot so I can figure out which ones are different and which ones are not. So you twirl down the option for descriptive plots, move paint or your factor into the horizontal axis, and you'll get something that looks like this. I have the error bars displayed in this example as well. The initial findings, the initial outcome that you get will be ugly because it's too compressed. But when you grab the lower right corner of this graph, this plot, you can drag it out to the right. And I showed this in the video. Just drag it out and it will resize and reformat itself, and then we can see each of the types of paint. So here's what happens. 1, or fast coat, is different than 2. We see fast coat has the lowest time, which is the fastest time. So it is the fastest drying. And the second paint is the slowest of these 4. You'll notice that paint 3 and 4 are almost identical in their times. But what does it mean that 1 is different than 2 but not 3 or 4? I guess you could think of it this way. If you only had 3 kinds of paint, if you had, let's say, I'll just call them paints 2, 3, and 4. If you were just comparing them, you wouldn't notice a difference in their dry time. Same thing if you had paints 1, 3, and 4. You wouldn't notice a difference in their dry time. But if you were comparing 1 and 2, you would notice a difference in their times. So that is the outcome, and it's sometimes harder to interpret. We would like it to be really clean, like these groups are always different than those. In this case, we just don't get that. But we do know for sure that the fastest dry time is with paint number 1, the slowest dry time is with paint number 2, and that there is a statistically significant difference between those 2. That's what you need to know for the assignment itself. Any other questions?
What we just covered is week 8's assignment, so this coming Sunday?
Yes. Yes, so that's starting today. Today is the beginning of week 8. So you have all week. If you want to jump on it right now, get it done before break, you can do that. Or you take whatever time you need this week. The Unit 2 test is also live. There is a study guide for that, and there are some data sets. So really you have 2 weeks to work on that Unit 2, we'll call it the midterm test.
When is its official due?
The midterm is due midnight on Sunday of week 9. So 2 weeks away. Let's see again.
13 days from now?
So the 13 days from now. And the assignment for week 8 is due on Sunday night of week 8. So I tried to make week 8 a little lighter. So there's really just you'll be doing more than one-way ANOVA, but you'll be doing the same technique several times. And that's really the largest part of what you're doing for this week. The rest of it, you can knock it out pretty fast, a little bit of reading. And then you can use the rest of the time. You still have plenty of time for your break. The rest of that time to study for the Unit 2 test. Study guide is posted along with that. The study guide contains all of the information that you will be tested over. So if you know what's on the study guide, there won't be anything that will surprise you, like, where did that come from? It's all right there for you. All right. And I guess one other thing to mention, I did include some class notes that cover most of what I've talked about in class, maybe in a little greater detail. So if you're looking for something on that study guide, you didn't remember it, didn't take a note on it, look in those class notes, because it'll be in there as well. Anything else before we wrap up? So a little shorter lecture today. So thanks for being here. Glad that you got to do this. Thanks for coming in, and I will see you next month.